So I'm excited to talk today about monitoring with everyone because it's one of my favorite parts of working on software systems. There's nothing more rewarding for me than seeing the code I wrote or the code my team wrote being used by real people in the real world. And in many ways, monitoring is what makes that possible. So when I talk about monitoring, I mean simply the practice of observing and checking the behavior and outputs of the software system over time. Basically collecting data about the systems that we run in production and observing and looking at that data over time. So I want to make the case to the folks here today that monitoring is a tool for software quality. Collecting data about the systems we build as they run in production is just as important as testing them out when we build them. So we'll talk about a few different sources of monitoring data, some guidelines for choosing tools to work with them, some principles on how to extract useful signal from the noise in the data that we collect, and finally, some guidelines on how to write effective alerts that work for your team. So to start, let's talk about why monitoring is useful. At 8th, if you've worked with us or read our blogs or know a little about us, you know that we really value software quality. Our development practices, our design principles are all focused on quality. And one of those core practices that we see as a foundation of building quality software is automated testing. A good unit test describes an expectation about how a software system should behave. When you execute it, it verifies that the system is working as expected. But if you've worked with automated tests for a while, you probably also realize that they do a lot more than just verify correctness. That's a huge part of what they do. That's super important. But there's a lot more that unit tests do. The active testing provides feedback on design. Good tests enable us to make changes to software with confidence. And they alert us quickly when a code change has an unexpected consequence. The expectations that we choose to encode in tests are also not just for ourselves, but for other people. They communicate our mental model of the system to others in a shared language. So testing is really about observing how a software system works while you're building it. And I think monitoring is about observing how a software system works while you're running it. So collecting data about the systems we run gives us a lot of the same benefits we get from tests, but in production. Monitoring enables us to write alerting rules that capture expectations about how the system should behave. Those rules can notify a human when something breaks, just like an automated test. So something like, I expect 90th percentile latency for the login endpoint to be less than 300 milliseconds is just as important, just as valid, just as useful an assertion as I expect the login endpoint to return a 403 when I post the wrong password. So just like tests enable teams to add new features, refactor code safely, monitoring provides a safety net for deploying our code and changing the infrastructure that supports it. Alerts and dashboards capture and communicate our expectations about the system, its components, and all their interactions. And in fact, I think a good monitoring dashboard is one of the best places you can look if you're a newcomer trying to understand the architecture of a software system. Having access to real-world data can give developers design feedback and surface insights that are difficult or impossible to collect outside of production. It's really hard to write unit tests that answer questions like, will our recommendation API survive a marketing email that goes out to 2 million people? Will the pagination widget that we built still work if there are 100 million rows in the database? Is the cache actually doing anything? Distributed systems tend to degrade and fail in complex, emergent ways that are really impossible to anticipate sometimes. But effective monitoring can catch some of them and provide the data we need to debug others. So if you take anything away from this talk, I hope it's this. Testing and monitoring are both tools for software quality on a spectrum of practices that spans the whole software lifecycle. If you care about quality, as many of us do, you should care about both. I really like this diagram from Cindy Sridharan, which puts these tools in perspective. Text might be a little small, but you can see sort of the whole spectrum of practices for testing, both in pre-production and in production. So over on the left in pre-production, unit tests, functional tests, component tests, fuzz tests, all the different types of testing that we tend to do in pre-production, all the way through to deploying integration tests, load tests, canarying during releases, monitoring during releases, exception tracking, and post-release testing, things like profiling, logging and eventing, monitoring, etc. So testing to me is so much more than just unit testing and the things that we do in pre-production. It's really building automated systems for software quality that go throughout the whole lifecycle of software, from pre-production and design through deployment, through release, and into production. So I think I said the O word a couple of times in there. So we should talk briefly about monitoring versus observability. If you spend a lot of time arguing with people on Twitter or Hacker News, you might see folks arguing about definitions or insisting that monitoring is old and busted and observability is what we all do now. So like most Twitter fights, I think there's a kernel of truth in there and something much more complex that's actually going on. So I think of monitoring as a practice. It's about collecting data about our systems and using it to verify that things are working. I think of observability as a characteristic of the systems that we build. It's about whether or not we can use the data we collect to look inside our systems and understand them. Another way to put this, maybe with credit to Donald Rumsfeld here on the right, is that monitoring is about known unknowns. The things that we know about, the failure modes that we can anticipate, we monitor. Observability is about unknown unknowns. We want to build the quality, the characteristic of observability into our systems so we can debug the kind of complex failures that we can't anticipate but will ultimately happen in production. And to go back to the metaphor of monitoring as similar to testing, I think of sort of testing versus working with an interactive debugger. Both of them have their place. Testing is sort of more like monitoring, right? You're making assertions about the behavior of the system, things that are sort of captured and automated in a particular way. But when I'm developing new code, when I'm working on code and sort of test driving a new feature or whatever, I'm not purely working with unit tests, right? Sometimes I want to get inside the system, understand what's going on. Sometimes I'll get a failure in a unit test and sort of not understand what's happening. You need to look inside to figure out what's going on. So maybe I'll jump into IPTV in Python or cry, something like that in Ruby to get inside my code and really observe what's going on. So observability is sort of that characteristic of being able to trace and understand and look inside and see what's happening. So both are important, both have their place. In some ways, monitoring, observability is sort of a superset of the concept of monitoring. So the goal of monitoring is to collect useful data about our systems in production. And let's start by looking at the data sources. There are many, many different kinds of data we can collect in many different ways, but I think these are 4 of the big ones. So logs, errors, metrics, and traces. So starting with logs. Logs are sort of like the coelacanths of observability data. They have survived for millions of years. Everything else descends from them, and they're still around somehow and surviving in the niche where they live. Just about everything emits logs, text data getting spit out, over some sort of line protocol. Processes, containers, databases, cloud infrastructure. And logs provide an immutable record of discrete events over time. I find them especially useful basically as an authoritative record of what happened when, right? Anything that has a timestamp and some text that we can parse really tells the story of what happened when. Logs take a few different forms. So here are some examples. They could be unstructured, just sort of free-form text data with a timestamp. So here's an example from a Terraform run on my local machine. You can see spitting out logs at various levels, info, debug, trace, and then some text that's doesn't necessarily follow a particular pattern or structure, right? We've got the Terraform version, CLI arguments, some other debugging information about what's going on. And a lot of the logs you work with are this way, right? If you're pulling in logs from systemd or Linux instance or wherever else you're getting logs, oftentimes you're working with something that doesn't necessarily have a specific and meaningful structure. They could be semi-structured, like these logs in the middle, which are from Nginx. So these have a meaningful pattern where each field, space-separated field in these logs, and then even within some of the fields, right, like this timestamp, have different meanings and represent different components, right? There's an IP address in here, timestamp in here, HTTP method and path, return code, some other things in here. So you're working with semi-structured logs, it's possible to kind of parse them and extract meaning based on the field values. And then finally, structured logs. Here's an example from a Docker container that's hooked up to FluentD. which is actually logging structured information, right? JSON data line by line. So typically in the real world, you're working with logs of all sorts, some unstructured, some semi-structured, some structured. And the goal is to sort of put them in one place and extract meaning from this narrative that's telling you about what happened when. Here's an example of the kind of tool you might use to search and interact with and browse your logs. This is Kibana. But other tools you might see in this area are things like Splunk, Journal-D, CloudWatch, if you're on AWS, or the classic Elasticsearch Logstash Kibana stack, which is often called you can see here, actually, Kibana has extracted, sort of taken an unstructured log here. I think these are Nginx or Apache logs, right? And used a pattern format, right, to try and extract some of the data out and actually make it more useful to search here, right? So it's extracted out things like creation time, message bytes, message URL, everything. So the second data source is errors. If you've ever worked back through an error stack trace, you probably know that errors contain a ton of useful data about the state of your code. Error monitoring tools capture these errors in a structured way, and they'll enrich it with context about your application. Many error monitoring tools provide things like local variables. They'll map errors back to the source code, so you can really look inside your system at the point when an error occurred and figure out what was going on. These kind of tools are usually configured at the app level, usually by wrapping your own code in a library that will capture and store and save all uncaught exceptions. In my own opinion and experience working with teams, there's really no higher value tool than error monitoring for a team that's starting from scratch. Error rates are one of the most useful metrics you can track in the first place, and error monitoring will immediately make that visible to your team when errors are happening. Many infrastructure failures also bubble up as application level errors. So things like database connection failures, API errors, request timeouts. Oftentimes those things throw a meaningful exception in your application level code. So you sort of get monitoring of that stuff. You can think of it kind of for free from an error tracking system. And good error tracking tools really give you a lot of visibility into system internals, where you can look at a stack trace, see local variable bindings, see what's going on. So error tracking shouldn't be your only form of monitoring. But if you find yourself in a situation where it is, I think it can go a surprisingly long way. And it tends to be a really high value investment of effort and time for your team. Finally, don't forget about the front end. Error tracking is really useful for JavaScript too, and has an increasing amount of behavior moves to the front end, using tools that integrate with JavaScript to do real user monitoring on the front end and figure out what's going on in JavaScript applications are just as useful as instrumenting and collecting errors from the back end. Here's an example tool for error monitoring. This is Sentry, but there are a number of others that do similar things, tools like Rollbar, Bugsnag, and others. Next data source is metrics. So if we think of logs as sort of the narrative of events that tell the story of your system, metrics are the quantitative indicators and summary statistics that represent those same events as numeric data. Usually in practice, metrics are time series data, meaning measurements that are taken at a particular frequency over a particular period of time. And working with numbers is great for a few reasons. The main one is that we can do math with them. We can apply what we know about statistics and modeling to do things like detect anomalies and make inferences and predictions about quantitative data. Secondly, metrics are really efficient. So a metric like 90th percentile latency is very information dense. That's a metric, a single number that summarizes thousands or hundreds of thousands of individual requests in a single statistic that says something meaningful about system performance. That information density is useful for the humans who interpret metrics. It's just a meaningful statistic that gives you a lot of information as a human in a single stat. But it's also really useful for the systems that we're using to store and transform and investigate metrics. It means that it's way more efficient to store them, transform them, query time series metrics, than to do things like reconstruct them from logs. That also makes metrics great for alerting because it's fast and quick and easy to query metrics and trigger alarms when they go out of bounds. So cloud infrastructure, monitoring, application performance monitoring tools all tend to generate a lot of metrics out of the box. But you can also collect custom metrics that track whatever you want. by instrumenting your code with your own tools and using tools like statsd, collectd to send whatever you're interested in monitoring to a monitoring server that you can then use. Here's an example metrics tool. This is CloudWatch metrics for an RDS instance in AWS. And you can see some of the metrics that basically come out of the box for a database instance in CloudWatch. So this is showing queue depth, write throughput, read throughput, write latency, read latency. And you can sort of access this all through AWS, through CloudWatch. So the last of the big four data sources is traces. And if you like logs and you like metrics, you're going to love traces. Think of tracing as a kind of logging that basically captures data about the whole lifetime of a request as it makes its way through the system. So tracing follows each request path through a software system. And at each step, these are also sometimes called spans. You'll hear about spans and traces. But basically, at each step along a request path through your system, we record and store some metrics and some metadata about the request. Usually, the most useful metrics are timing, so you can just get a sense of how much time a request spends in the different subcomponents of your system. But you can store all kinds of metadata and metrics at every step of a request. So think of it sort of as like the best of both worlds, right? It's like a log that's capturing the path, capturing what happens when, but we're also collecting metrics at every step of the way. So by using traces, we can automatically generate visualizations like service maps that show request paths, bottlenecks, and dependencies between the services in your system, and things like this flame graph here, which shows the amount of time that was spent in each step. So this is a Rails request. This is an example out of Datadog. And you can see sort of the full length of the span up at the top, rack request, shopping cart, controller, checkout. You can see there are sort of three subsystems that it's interacting with here. I think one is a sort of an authentication system. One is the Rails controller itself. One is actually making a call to an external API. You can actually look and trace. There's something going on down here at the bottom, which is too small for me to actually see. It looks like something with product recommendations or an email API or something. But you can see sort of the whole story, the whole history of this request, as well as stats about the amount of time that's spent in execution for each step of it. So traces are very cool, very useful, but they can require instrumenting all the components in your system to collect information about every span. That can get more and more challenging as your systems get more complex, more distributed, have more and more moving parts. But the good news, at least in my opinion and experience, is that for sort of simple systems, the type that I'm usually working on, you can get pretty far out of the box by using like an APM tool or something like some of the out of the box tools that are available and that I tend to use. So some tools for tracing, things like Zipkin and Open Tracing, which are two open source tools. X-Ray, which is the AWS tracing offering. Honeycomb or APM tools that are built into other offerings, so like Datadog, which I'm showing on the right here. So we have all kinds of types of data we can collect, and there are even more tools to choose from to collect them. So a few principles for choosing tools here. I'm not going to recommend specific tools in this talk because that decision is just super context specific to your team, to your application, and there are so many of them to choose from. But I do want to suggest a few principles for choosing monitoring tools. So the first one is to embrace specialization. It can seem unnecessarily complex sometimes to add multiple tools to your stack to collect logs, to collect errors, to collect metrics, to collect traces. But specialized tooling exists for each of these data sources for good reason. I found that tools designed specifically for each type of data are more efficient and tend to be easier to use. In practice, I've seen lots of teams who are missing one or more of these tools and sometimes don't realize it. And that usually presents as a strange or painful workaround that sometimes teams aren't even aware of. So if you find yourself scraping logs for stack traces and trying to look back to see what happened with a stack trace, you're probably missing a component of the monitoring ecosystem. You probably need an exception monitoring tool. If you're trying to do complicated aggregations in Kibana and your dashboards keep timing out because you can't load them, it's doing complex aggregations and calculations, you probably want metrics. If you're throwing a custom exception so you can see it in Sentry, but there's nothing actually wrong, you probably need better access to your logs. So think about whether and where you have the right tool for the job and embrace specialization when you choose tools. Second, always remember that monitoring and observability should be about reducing the complexity of your system. And think carefully about whether the observability and monitoring tooling you're choosing reduces overall complexity. For me and my teams, that usually means using hosted software as a service tools, even when they're thin wrappers around open source tools. Many open source observability tools are themselves distributed systems. They often involve really fun and shiny tech like log streaming pipelines and time streaming databases, time series databases. These things are like catnip for people who like distributed systems, who like observability. But don't fall for that. Think about the complexity and maintenance costs of your tooling before you do it yourself. Hosted services can seem expensive, and they are expensive, but measuring them against the opportunity costs of the engineering time you'd otherwise need to spend on them can put them in better perspective. Yeah, I'll emphasize that. Like I never want to, I never want to maintain an elk pipeline ever again. Finally, choose tools that empower humans, like whatever that means for you and your team. But the point here is that usability of these tools matters. Observability tools are meant to empower your team to explore the internals of the systems they build and to ask and answer questions about their behavior. And the tools just aren't useful if people don't use them or if they're too complex to use. So if a tool isn't working because the query language is complicated, the metrics it collects aren't working for you, whatever the reason is, don't be afraid to try something else. There are so many tools out there. There's so many options. And the core point here is to empower people to answer questions, not to force people into whatever structure a tool is specifying for them. So remember that the goal of these tools is always to serve humans first. Okay, so we've chosen some tools, whatever they are. We've got a tooling up and running. We're collecting logs, metrics, errors, and traces. We're spending half of somebody's salary on log storage. Now what? Once we have our hands on monitoring data, the goal is to extract useful signals from noisy metrics and make them visible to human operators and automated systems that interpret them. So to go back to the testing metaphor, I like to think about an observability pyramid that's kind of like the testing pyramid. So credit for this diagram, and this one goes back to Cindy's for drawing too. At the top of the pyramid, we have alerting. We want to use some of the data we're collecting to catch critical failures and notify someone when something goes wrong. Of course, in order to alert about those failures, we have to be able to anticipate them in the first place. So this very tip of the pyramid only applies to our known nodes. And alerting is really expensive. It's intentionally interruptive by design. So we only want to alert on a few things we really care about. That's why it's the tiny piece at the top of the pyramid. So next in the section called overview here is using our monitoring data to summarize and expose the overall health of a service. This layer is really about communicating to other humans, building dashboards and visualizations that augment our understanding of the system and that can expose where to start looking when something goes wrong. And finally, the foundation of the pyramid is using monitoring data to debug, to profile, to analyze, and to explore. So this vast and sort of large foundation of the pyramid is about using monitoring data to explore unknowns. This is really where observability comes in, right? Being able to get into tools and explore and ask and answer questions about our system. So up at the top, alerting, dashboarding, and overviews are proactive. We typically configure alerts, build dashboards based on a few curated metrics that present a simplified mental model of how the system works. The rest of the pyramid, the bottom, is reactive. We debug, profile, and analyze when something happens that we want to explore and understand. So we can take a look at an example dashboard. Here we go. This is a real example dashboard. We can see it's showing like the status of all our teleporters. We've got a business guy who's looking at some ones and zeros. I'm just kidding. This is the image that was on the meetup for this talk. Here's a real example dashboard. This is GitLab's triage dashboard, which is designed to visualize all the most important indicators about the high-level health of their system and be the first place to look when something goes wrong. I think this is really cool. GitLab is sort of a notoriously transparent company, and they've actually exposed their Grafana dashboards here online. If you just Google, there's a link in here in the slides, which we'll send out, but you can view all their configured dashboards for the GitLab service as a whole, just directly through Grafana. So I took a screenshot of this morning. It's pretty interesting, but you can see they're exposing some of the metrics that are most important about how GitLab is working. So status of their Sidekick queues, Sidekick load by priority, I'm not sure what Giddily is, right? But something that's using gRPC, tracking an error rate, and a latency metric, and load averages across their fleet, and errors by backend type. We'll talk a little bit more about some of these signals in a second. But this dashboard is an example of sort of designed to be the place that you go and look first when something's gone wrong to point you towards what could be an anomaly or an issue, or start guiding that process of diagnosing an issue or an outage in production. And actually, you can see something happened earlier today, right around 1 p.m. UTC. You can see elevated 500 request errors in one of these backends here. So from looking at this dashboard, you can see, okay, that's a clue to where to start digging in around what might be the cause of that outage or those errors. And in combination with this is hard to visualize and show here, right? But there's alerting at the top of the pyramid here as well, right? Probably alerts configured on some of these important metrics where when they exceed the threshold, like seeing this big spike in 500 requests, paging somebody who's on call, sending a notification to Slack, something like that gets the attention of a human operator to say, hey, come take a look at this issue. So in fact, some of the things on this dashboard are what are called the golden signals. The goal of alerting and dashboarding is to focus on a few high-level metrics, and golden signals are a great place to start. So the Google Site Reliability Engineering book, which is a great read, has a really good chapter on monitoring that introduces these. And as they say, if you can only measure 4 metrics of your user-facing system, you should focus on these 4. So the signals are latency, errors, traffic, and saturation, which I remember with the acronym LETS, like Let's Potato Chips here on the right, a fictional brand of potato chips from television and movies. Ask me sometime about the Let's Potato Chip verse if you're interested. So errors, latency, traffic, saturation, these are all great high-value metrics that can apply to just about anything. And one of the first things I do if I'm setting up monitoring for a new system is create dashboards for each of these metrics for each component of the system. If we go all the way back to GitLab triage here, you can see that they have each component. So their front-end load balancers here at the top, Rails, gRPC, Sidekick. If you look at this, the databases are next under here. And they're visualizing some of these golden signals directly in this dashboard, right? Exposing them for each component of their system. So yeah, these dashboards are like one of the first things I'll do on a new team, and one of the best places to look to start sort of extracting that signal from the noise and giving people useful information that they can use to understand how things are performing. So we can walk through each signal and some examples of what you might monitor for each. So errors are pretty easy, pretty straightforward. You might count HTTP 500s at your load balancer. You might count exceptions originating from your app server. You might count timeouts if they're originating from the database. So the idea here is that each of these metrics, errors, can apply to different components of your system, but the shape that takes might be different metric depending on the different component. It will be different for a load balancer versus an app server versus a database. But just about every system or subsystem exposes something that we can count as an error. So the second signal is traffic. Traffic measures how much demand is being placed on the system. That could be something like HTTP requests per second for a load balancer for a web server. Something like queries or transactions per second for a database. Or even something like network I/O if you're doing like an audio streaming system or a video transcoder, something where traffic is measured by network I/O. Again, any of these metrics could be good measurements of traffic. So you have to think through your individual use case, your individual component, and figure out what metrics are available, what data you're collecting, and what you can use to measure traffic. The third measurement, which is the trickiest one, is latency. So latency is the time it takes to serve a request. And it's much trickier to measure this than it might seem, largely because this is one of those metrics that summarizes many data points into a single number. So it can be tempting to want to use an average to measure latency, but averages can be really misleading when it comes to latency metrics. So instead of averages, it's best to measure latency using what are called percentiles. So the nth percentile of a distribution is the value below which we expect n percent of all observations to fall. So concretely, saying something like 90th percentile latency is 200 milliseconds means 90% of all requests take less than 200 milliseconds. we say something like 95th percentile latency is 350 milliseconds, that means 95% of all requests we've measured take less than 350 milliseconds. So it's pretty common to measure 90th percentile, 95th percentile, and 99th percentile latency, which sort of give you like increasingly worst case scenarios of latency. Unfortunately, most monitoring tools will automatically calculate percentiles from request latency metrics for you, so you don't necessarily need to do the math yourself. This is a great place where we can do math with our metrics that tells us useful things about latency. This image over here on the right is pretty cool. This is from a website and maybe even a book that Brendan Gregg put together. But this diagram is visualizing MySQL command latency for 35 random commands over 35 random servers that he selected. And what he's done here is lined up all these latency distributions so that the mean, this black line through the middle, is the mean for each distribution. You can see these different distributions of request latency, which are really common out there in the real world, right? We have a few different types of request latency. So these ones down here at the bottom have a big hump over on the left and then a long right tail. That's a pretty realistic distribution out there in the real world. You know, the challenge using averages for latency is that very few things where we're actually measuring latency are normally distributed, which is where averages work best. You know, if it was normally distributed, we want to see the average sort of right in the middle of the biggest hump in the distribution. But a lot of software systems have these long right tails, right? You think of like network effects within, say, an API endpoint, right? In the real world, we have lots and lots of these sort of long-tailed power law type distributions, right? Somebody might have one post, but a very small subset of your users might have like thousands or millions of posts, right? So an API endpoint that like returns all posts will be one of these long right tail type distributions. Another very common one is multimodal distributions. So some of these in the middle. Here's one with 3 peaks, and a few up here with 2 peaks as well. Those are also really common in terms of request response latency. If you think about something like an endpoint or query that takes a lot of work, right? It takes a lot of computation to do. The first thing you often do with those queries is cache them, right? So you'll get a response latency distribution frequently with an endpoint like that, where if you hit cold cache, right, you're doing that calculation for the first time. It'll take a long time. It'll be slow to return that result. Once you've calculated it, put it in the cache, subsequent requests hit a hot cache, and you'll see a much faster response time. So you can get these distributions that are multimodal. And within those, you'll see the average, like for this example, sits right in the middle. It's not a very useful metric, right? We really want to know about the worst case latency when we're hitting a cold cache. So anyways, the upshot here is look at percentiles, look at what are called P90, P95, P99 response time when you're trying to measure latency. There's a really good talk out there called Everything You Know About Latency is Wrong from Strange Loop, and I recommend checking that out as well. So the final of the 4 golden signal metrics is saturation. Saturation measures how much extra capacity your system has before it hits a hard resource limit like memory, I/O, or disk space. So oftentimes you can measure this directly, right? If you're monitoring like a server instance, you probably have direct access to memory usage and disk space. You can take a look at how much disk is left, how much memory is being used over time. But in other cases, you might actually have to use indirect signals for saturation. So something like a load balancer, you could use HTTP 503 errors over capacity. That'll be like a leading indicator that something is saturated downstream of the load balancer. Another good saturation metric for a lot of systems is actually latency, P99 latency. Oftentimes, looking at 99th percentile latency over a small time window is a leading indicator of saturation because many services will degrade rapidly as they approach capacity. So it can be a little bit trickier to measure saturation through some proxy metrics, but usually you can find a good saturation measurement for most of the subsystems. So thinking through each of these golden signal metrics for every component and layer of your system is a fantastic place to start extracting signal from the noise. Once you move beyond the golden signals to monitor other metrics, it's useful to think in terms of symptoms versus causes. So going beyond those metrics, as you start thinking about other things you might want to monitor, I find that this definition of what's a symptom versus what's a cause comes in very useful. So here's another quote from the SRE book. Your monitoring system should address two questions: what's broken and why. The what's broken indicates the symptom. The why indicates a possibly intermediate cause. What versus why is one of the most important distinctions in writing good monitoring with maximum signal and minimum noise. So here's some examples from this book as well, of symptoms versus causes. So a symptom could be something like, I'm serving HTTP 500s or 404s. The cause of that might be that database servers are refusing connections. The symptom might be that responses are slow. There could be a lot of causes of that. CPUs overloaded by a bogus sort, an Ethernet cable crimped under a rack. Users in Antarctica aren't receiving animated cat GIFs. That's a symptom, right? It's like written from the user perspective. But the cause of that is something downstream, right? Your content distribution network blacklisted some client IPs. The symptom might be that private content is world readable. You didn't need to expose it. Cause might be that a new software push caused ACLs to be forgotten and allowed all requests. So high signal alerts are usually focused on symptoms. I think there's an interesting user empathy aspect here, right? A good way to think about them is to sort of put yourself in the user's place and consider what they see. Ultimately, users care about things like, I'm seeing an error, responses are really slow, the login page is broken, not things like whether CPU on a web server exceeded an 80% threshold. It's useful to have visibility into causes in order to debug symptoms. So you should be tracking causes as well. Hopefully you have enough observability in your system to go back and track symptoms, track down the causes related to symptoms. But oftentimes causes are too noisy to really make good alerts to call out, hey, something's wrong, to interrupt a human to say, take a look at this. So dashboards tend to be a good place to expose your causes. Alerts are a great place to expose your symptoms, to monitor for symptoms. So to go even further with metrics is the concept of capturing custom metrics as well. So we can take that idea of monitoring for the user, right, monitoring from the user's perspective, even further by capturing custom metrics that are related to our application and domain. This usually requires instrumenting your application code a little bit, but it tends to be pretty painless using custom metrics through most SaaS monitoring tools or setting up an open source tool like StatsD that can do this. And you can get really great visibility into the symptoms that users care about. Those things like the login page is broken, something's going wrong. Specifically things like which features are working by actually tracking interactions with those features through your code and instrumenting the application itself. So you don't have to stop with the metrics that are just generated out of the box, right, by your monitoring system, your cloud provider, whatever it is. You can actually instrument your code and collect some of these. So consider tracking metrics like active users, successful and failed logins, new signups, number of comments that are posted, number of checkouts that are completed. Anything that's meaningful in your context, in your domain, in your application, you can collect a metric for that just as easily as you can collect a metric for the state of your infrastructure or other components within your system. So down here is an example of using StatsD and Python to instrument, a really simple login function here, right? And we could just do something like, if password is valid, we'll call out to the StatsD client and increment a login success counter. If the password fails, right, if the login fails, we'll increment the login fail counter. And that can generate a dashboard like this that can show us something really useful about the state of logins, right? Here in the middle of this, we can see that there's a big spike in failed logins sometime in the middle of the night. And I'd say even if instrumenting your code is challenging for your team, right, or if there are sort of obstacles to instrumenting your code, which there can be, right? It can take a lot of effort to add a tool to go back and find all the places you want to measure something and do instrumentation. But you can often do this kind of monitoring sort of on the cheap by thinking about the things that you can monitor that are exposed through your tools, right? So you can craft monitoring rules or metrics that are watching specific API endpoints or catching specific errors, right? In many applications. So you think about this login endpoint again, you get something kind of like this by monitoring, say 403 errors versus 200s on the login endpoint. If that's exposed through your monitoring tool, you can get a nice metric that says something meaningful about your application and your domain itself. So we're getting to the top of the pyramid. And to wrap up, let's talk a little bit about alerting. This is the high stakes, high impact, very tippity top of the observability pyramid. I personally think getting alerting right and doing it humanely is a serious responsibility. This is when we wake people up at 2 a.m., pull them away from the dinner table, and tell them they have to fix our bad websites. So when I think about alerting, I like to follow a set of principles, specifically pulled from an article that's really good. This talk actually sort of originated because I think this article is great and I want people to read it. So if you take one thing away from this, well, I guess we take two things away. If you take one thing away from this, think of monitoring as a tool for software quality. If you take two things away from this, go read this article. I think it's really useful and one of the most like information-dense things you can read about monitoring. But effective alerts, should be, when I think through creating alerts, I think through these principles for effective alerting, which are that they should be urgent, actionable, unique, focused, and real. So let's walk through each of those step by step. First, if an alert isn't urgent, we shouldn't interrupt a human to deal with it. And if it might become urgent soon, but it's not urgent right now, consider opening a ticket or logging it in some other dedicated location to review later. If an alert isn't actionable, you probably don't need it at all. If nobody does anything when an alert fires, and noting, hey, the alert fired again is not doing something, is probably not useful. This can happen more often than you think. If an alert isn't unique, you're probably just generating extra noise. So especially with overlapping monitoring tools, this is a bit of a trade-off with choosing the right tool for the job. It can be easy to generate duplicate alerts from different systems. So to go back, think about which one of those alerts is the symptom and which one is the cause, and try to remove duplicates. Usually you'll be able to find that one of them is more user-focused, more the symptom, one of them is the cause, and try to remove one of the duplicates. Good alerts are focused, meaning that they go directly to the people who need to see them. Whether that's sending a page, sending a Slack notification to a specific channel, or opening a ticket, too many alerts going to too many people can fatigue the whole team. And finally, alerts should be real. This is surprisingly challenging, surprisingly easy to talk about in principle, but surprisingly challenging in production. At their best, false positives are distracting annoyances. At their worst, they can create chronic background noise that eventually causes real alerts to go unnoticed. So if you find yourself with an alert that's a false alarm, fix it or remove it right away. And this can be surprisingly hard in practice. Software changes very frequently. You find that alerts tend to lag behind the pace of code changes and software changes, right? It's much faster for many teams, especially if they're following good continuous delivery and continuous deployment and development practices. Code can change a lot faster than your alerts can. So it's easy for alerts that used to be useful, used to be providing a lot of signal, to sometimes turn into noise over time as the circumstances of your application change. So always be ruthless about pruning false positives in your alerts. So I hope I've made the case today to you that monitoring is an important tool for software quality. I hope I've given you some principles, some practices, some concepts about tooling, and places that you can get started monitoring and observing your own systems. Thanks, everyone.